Good day, everyone. So welcome to the week 8 of our course ECE 6171 or Fundamentals of Mixed Signals and Sensors. For this week, we have convolution and correlation as the topic, but this module will be divided into 2 weeks. Okay, so first we will start with convolution. So for the learning outcomes of this module, we have by the end of this module, a student is able to, number one, understand the concepts of convolution and deconvolution, and number two, differentiate the properties of convolution and correlation. Okay, so this one will be for this week, and this one will be for the next week. So this will be our topics to cover. For this module, we have convolution and deconvolution, properties of convolution, correlation, and density spectrums. Okay, so before we start, just a little recall about our previous topics. Okay, so we started with signals, of course, introduction to signals, then amplifiers, signal flow. Then last week we had Z transform, wherein it is a method of transforming a time domain signal to frequency domain signal. We also segued with the refresher course for the Laplace transform to help us understand Z transform better. Okay, so this time we will have convolution. So for the definition of convolution, convolution is a mathematical operation used to express the relation between input and output of a linear time invariant system. It relates input, output, and impulse response of a linear time invariant system. So this is the convolution operation. We have the star. So this is different from multiplication. Okay, because we're dealing with signals. Okay, so in this representation, we have y of t as the output of the linear time invariant system, x of t as the input of the linear time invariant system, and h of t as the impulse response. So we have two types of convolution. We have continuous convolution and discrete convolution. Okay, so we will discuss one by one what are those. And we have deconvolution here. Is the reverse process to convolution widely used in signal and image processing. So before we proceed here, let's discuss convolution first. What does convolution mean? Okay, and why it is important. For example, we have two signals. We have what we call h of t, and h of t looks like this. Okay, so this is time domain. So at time 0, let's say we have this signal. Okay, so this signal has a height of 1, length of 2. Okay, and this one is also 1. And we have an input signal. This is the impulse response. Okay, so what do we mean by impulse response? Impulse response is when, or the response of the system whenever there is a input stimuli. Okay, what do you mean input stimuli? We talked about it in our sensor. So that is the element that will activate our sensor. For example, it can also be a switch or whatever device to activate the sensor or the system. Okay, for example, we have h of t here. This is the impulse response. We have x of t. This is the input. Okay. So for our input, let's say we have here at time 0, we have a signal with a height of 1. We have an impulse signal at the height with a height of 1 at time 0. Okay. So when we say convolution, let's do this. Also at time 2. Let's do it like this. So you can see better what does convolution do. So the working equation or the basic concept of convolution is we have the input signal convoluted with the impulse response. Okay. So in this case, what happens is whenever there is an whenever there is an input signal, our impulse response will be activated. Okay. So in this case, in x of t, there is an input signal at time 0. Meaning at time 0, our impulse response will be activated. Same with time 2. This might be in seconds. So at time 2, there is also an input signal. Therefore, our impulse response will also be activated. So what will happen, or what does the convoluted signal looks like? Okay, so it will be looking like this. You have time 0. Okay. Time 1, time 2, time 3, time 4. So this is convolution is kind of a multiplication, but it is for signals. Okay. So what will happen is we will multiply this with this. Okay. So we will multiply 1 with the impulse response. So since the multiplier is 1, so the impulse response will be the same. But the impulse response is activated at time 0. Therefore, in our convoluted signal, we will have an impulse response from time 0. Okay. Also, the signal we also have an input signal at time 2. So therefore, the impulse response will also be activated at time 2. Okay. So this is now our convoluted signal y of t. Okay. So we can say that the convolution is the combination, or rather, the multiplication of our input signal and our impulse response. Okay. So the impulse response activate, or rather the input signal activates the input response, and the convoluted signal is the output of the interaction between our input and impulse response. Okay, so let's proceed. I will switch between the module and the PowerPoint presentation. So okay. So this is the block diagram of our continuous convolution. We have the input going to the system, and then we have an output. Same with the discrete convolution. So again, input, impulse response, output. Input, impulse response, output. So that is the basic structure of our convolution. Okay, what's next? So this is the continuous convolution. This is the working equation of our continuous convolution. Okay, so let's try to understand where did this equation came from. Okay, so using this, let's do another example. Let's say we have an impulse response, the same impulse response. Let's use the same example. Okay, so we have again a triangle from 0 to 2 with a height of 1. And we have this input signal. Our input signal is not a single pulse, but is a continuous signal like this. Okay. Say okay. So this will be our input signal. It has a height of 1 so that our representation will not be that difficult. Okay. So what will happen here is for the convolution of these two signals, okay. So again, the input signal is what triggers the impulse response. So in this case, dx of t again will activate h of t. So what will happen is for this type of input, our earlier example is a pulse signal. For this type of input, which is a continuous signal, okay? So every time, remember our discrete signal, we can divide this into different, we can divide this into pulses like this, okay? Remember the difference between our continuous signal and discrete signal. Meaning, in a continuous signal, there will be a large number of input or pulses. Okay, so it's not just a single pulse. So if we will draw the convolution between x of t and h of t in this case, so we will have so many inputs. So in this case, we have this one. Okay, this is for time 0. Then next, for this arrow, we will have this one. Okay, for this arrow, we will have this one, and so on and so forth. Okay, until we see that the shape of the convoluted signal resembles the input signal, but this time it is filled with the pulse signal. Okay, so this will be a lot of triangles. Okay, So this is the convoluted signal. But again, this is a lot of input, okay, that we are trying to add on this signal. Take note, here, what happened is we just we added the convolution of this with the convolution of this, okay? So we added them. This is the output. In this case, we're also adding them, but there is a lot of impulse signals, okay? So what again is the operation when we try to add a lot of entities? So we have the summation, and integration is also a summation, okay? So in this case, we have the summation of the convolution of all the convoluted signals, or we have the summation of all the convolution that is happening between our signals. Okay, so I forgot to mention one thing. No? This part, okay, is activated when time is equal to 0. Okay. So this is activated the time is equal to 0, meaning this is y of 0, okay, x of 0, time 0. Okay, so the one that is dictating the time is the input signal. Okay, because the input signal will activate the impulse response. So the impulse response will only what is the term again? Not scale, but will adjust according to the input signal. So what will happen here is at time is equal to 2. Okay, you have y of 2, x of 2. Okay, and then what will happen here? Since this is time is equal to 2, so this will be equal to t minus 2 equals 0, right? Okay, so we will write here t minus 2. Okay. Wait, I forgot to write h. Since the impulse signal moved from 0 to 2, so t minus 2. Here, the impulse signal is still at 0, so there's no changes in t. Okay, and then the convoluted signal, which is y of t, is the sum of all the input signals, okay, which is y of 0 plus y of 2. So this is the output. Now, that is the case for minimal input signals like this one. We only have two inputs, two pulse inputs. So we can discretely add all the signals. But in the case of this one, where there is a lot of pulse signals, since the input is continuous, right? So we will have a lot of entities to add. So it is a bad idea to add them one by one, but we will use our summation process. And the summation process, again, is integration. So we'll use integration for this one. That will be x of t. No. As you've seen, the t on h remains, but the time for our input signal is changing depending on what time signal are we dealing with. So let's name that time signal as tau. Okay. Greek letter tau, that is the entity being used. So we have tau, okay, convoluted with h. Okay, then t minus tau. D of tau. Okay. Since this is integration, we have our limits, of course, from negative infinity to positive infinity. So this is our working equation for the convolution. This is the representation of convolution. This is our working equation. Again, this is derived because we are adding all the convolution within our input signal. Okay. So next, we have our discrete convolution. So what is the difference between discrete convolution and continuous convolution? For the discrete convolution, the input signal is discrete. At the same time, the impulse signal is also discrete. Okay? For example, we have this one. We have our h of t. Let's say we have this we have this one. We have -1 and 1. With a height of 1. This is our h of t. This is discrete, so h of n. Next, we have our x of n here. Okay. Let's say our impulse signal is this one. We have a 1 at 1 and a 1 at 2. Okay. 2. Right. So this is for our discrete. Now, the representation of discrete is x of n convolution with h of n. So y of n So notice the difference. Here the impulse response is discrete as well as the input. In the continuous convolution, the impulse signal or the impulse response is continuous. And the input signal can either be an impulse or continuous as well. Okay, so we have this one, x of n, h of n. If we combine or if we do convolution for both our signals, what will happen here is that, okay, we will have to do one by one. So let's wait, I'll transfer this one here below. Transfer this here. Okay, so what will happen is we will try to analyze for each input pulse. Okay, so we will analyze this for x of 1 first. Okay, so what will happen to our signal during x of 1? So at x of 1, if this is our impulse response, so what will happen is at 1, okay, at 1, we don't have a signal at this point. Okay, so at 1 there will be no signal, but there will be a signal here with height 1 from this, and a signal here with height 1 from this. Okay, so maybe to lessen your what do you call this one, confusion, I'll just add another signal here at time 0. Okay. So again, this is our h of n. We have 3 impulse signals. So 1. Then at x of 2, so this one, what will happen to our impulse is, okay, so at the time 0 will be at 2. Height 1. Then the negative 1 will be here at 1. Then this one will be here at 3. Okay, so what happened is our input signals 1 and 2 became the 0 of our impulse response. Okay, since the impulse response has 3 pulses from 1 pulse on each side of the center, so this is the output. Okay, then the ground output of our discrete convolution is that we will add this 2 signals from each input. Okay, so our y of n now will be equal to we will have this one 0, 1, 2, and 3. Okay, so at 0, we only have 1 impulse signal here with a height of 1. Okay, this is for 0. At 1, we have 2 impulse signals from input 1 and input 2. Okay, each with a height of 1. So we will add this, giving us a height of 2. Yep. Okay, then at time 2, we have 1 and 1, so a total of 2. Then at time 3, we have a 1 here, nothing here, so 1 plus 0. So we have 1. So this is our y of n in this discrete convolution. Can you still see this one? Okay, so let's go back. This is our impulse response. This is our input signal. Okay, then the step is to process each input signal. So from our x is equals to 1 or x at time 1, this, okay, or instance 1 because this is discrete, the 0 of the impulse response, the right side pulse, the left side pulse. At time is equal or at n is equal to 2, this one, okay, 0 at 2, right side pulse, left side pulse. Then the y of n or the output is we add all of the signals. So we have 1 here, not 0 here. So 1 plus 0 is 1. We have 1 here, and we have 1 here. So 2, 1, and 1. So 2, 1, and 0, 1. Okay, so that is for our discrete convolution. Okay, then this is our working equation for discrete convolution. Still the same with our continuous, but instead of the t and tau, okay, so t will be replaced with n. Since this is discrete, we are not counting time, we are counting the number of instances. Okay, we've explained it in the discussion of discrete and continuous signals. And then k instead of tau. Next, we have the deconvolution. Yep, deconvolution is the reverse process to convolution. So after deconvolution is the reverse. So we will separate x of t and h of t. We will separate the input signal and the impulse response. So next, we will discuss about the different properties of convolution. Okay, let's try here. Yes. So for our commutative property, or rather, sorry, for the properties of convolution, first we have commutative property. Okay. So x sub 1t convolution with x sub 2t will also be equal to x sub 2t convolution with x sub 1t. Okay, so let's to help us understand the convolution better, let's treat it as multiplication, but not really. Okay, there are some common characteristics between multiplication and convolution, but most of them will apply to our properties. So first, again, we have commutative property. So whether we do convolution from input signal to impulse response or impulse response to input signal, so the output will be the same actually. Okay. So for example here, let's go back to our very first example. If we will reverse this one, if this will be our x of t and this will be our h of t, okay, what will happen is for this signal, we will have this impulse response. So from time 0, we will have impulse response of 1 times 0 here and 1 times 0 at 2. Then at this impulse response, okay, since this is continuous, we will treat it as continuous. Then from this input response, we will have an input here, this times this, so this one, also at starting from 2. Then this one, this times this, also at 2. This one, this, and this, and so on and so forth. So if we will reverse our impulse signal, impulse response, and our input signal, the convolution will actually be the same. Okay, so that's it for our commutative property. Next, we have associative property. So if we have multiple signals for convolution, we have here 3. So whatever order we will do in doing the convolution will be, we will be having the same output, okay, as explained from our commutative property. Next, we have distributive property. This is a typo. This is our distributive property. Okay, so this looks the same almost with our multiplication, but let's try to show you why, or give you a better idea why our distributive property applies to convolution. For example, we have here 2 impulse responses, so H1T and H2T. Okay, so if we will do convolution with these signals, we will do convolution with x of t as the input. One impulse response is H1T, the other impulse response is H2T. Then let's say the output here will be x of t, H1T, x of t, H2T. Then this is the output. The next thing we do is we put this in another device or other process. Other meaning we add 2 signals. Adding and convolution is different. Okay, I think you're already familiar with adding. It was discussed in other courses. Okay, so we will add this. So we will have x of t H1T plus x of t H2T. Okay, but if we will do it this way, okay, we will do the other process first on the impulse responses. We will add these 2 signals first. Before we do convolution with x of t. So the output will be the same. Okay, so that is for our distributive, this one, distributive property. Okay, next we have the shifting property. Okay, shifting property. So if we shift our starting point, the convolution signal, the starting point of our convolution signal will also shift. Okay. How do I do this? Let's just take this example. So instead of having an input signal at 1, if we will shift this signal, okay? If we will shift this signal, for example, if we will shift our input signal, let's say instead of time 1 and time 2, so we will shift them to time 3 and time 4. So what happened is our input signal moved by 2 places. Okay, 2 places, so n minus 2. Okay. Instead of our time 0 being at 0, we transferred our time 0 to 2. Okay, so instead of n equals to 0, our n now, rather, so instead of our k 0, our k now is equal to 2. Okay, so it now becomes n minus 2. So since the input signal shifted by 2 places, so all of this will also shift by 2 places, right? Also this one will also shift with 2 places. So therefore, our output will also shift with 2 places because one of our signals has shifted. Okay. So that's for the shifting property of our convolution. If one of the signals is shifted, the output will be shifted. It doesn't matter if it's the impulse response or the input signal. Here, if both, okay, if both signals are shifted, so both shifts will also reflect on our output. Okay. In this case, the input signal has shifted. The impulse response has also shifted. So both shifts will also happen to our output. Okay. So that's for the shifting property of convolution. Next, we have convolution with impulse. Pretty much the same with our shifting. Convolution of unit steps, the same with our shifting. Next, we have the scaling property. Okay, so scaling property is pretty much similar with let's see. Scaling property is, well, we multiply a scalar quantity to our time. Okay. We multiply a scalar quantity to our time, both on our input signal and our impulse response. So the output signal, okay, will also have its time scaled with the same scalar quantity, and its magnitude will be multiplied by 1 over the absolute value of A. So that's for the scaling property. We will not try to prove this for now because we will encounter this later with an example. So we will not go deeper into this one for now. Next, we have the differentiation of output. Okay, so notice that when we differentiate one of the inputs, either the input signal or the impulse response, okay, so the output is also the same as differentiating the output signal. Okay, again, differentiating one of the inputs, either the input signal or the impulse response, the output will also be differentiated. So that is the differentiation of output. Next, we have the limits of convolution or convoluted signal. So if two signals, wait. I'll just try to look at our module. Okay, so we have a note here. Good thing we looked at our module. So we have a few notes. Number one, convolution of two causal sequences is causal. Convolution of two anti-causal sequences is anti-causal. Convolution of two unequal length rectangles results a trapezium. Convolution of two equal length rectangles results a triangle. A function convoluted itself is equal to integration of that function. What do you mean by the term causal? When we say causal, that is a system or a sequence in which all the values at the negative is 0. So the only positive values, or rather the only from 0 to the positive values, it will have a output. Okay, so that is causal. Anti-causal, of course, is the opposite of causal. So the negative values will have outputs. Okay. Convolution of two unequal length rectangles results a trapezium. Convolution of two equal length rectangles results a triangle. Should I make an example here? You can search for this one. This is the most common example when you search for convolution. Two rectangles, two unequal length rectangles and two equal length rectangles. So that will be your own assignment to search for the convolution of these signals. Okay. Next, we have the limits of convoluted signal. Okay. So if two signals are convoluted, then the resulting convoluted signal has the following range. Okay. So the sum of lower limits, this is the range, and this is T, I mean, and then the sum of upper limits. For example, we have here two rectangles. So one rectangle has a lower limit of -1, the other is -2. The upper limit of one is 2, the upper limit of the other is also 2. Okay. So to find the limits, So we add the lower limits, -3. We add the upper limits, 4. So the range of our convoluted signal is from -3 to 4. Okay? Oh, we can try to solve this one. So we have two rectangles. So our h of t is from -1 to 2. They have the same height. So -1 to 2. Height of, let's say this is height of 1. Then our x of t has a height of 1 as well. But it's from -2 to 2. So if we do the convolution of this one, I mean, if we draw the convolution, h of t. Again, this is multiple pulse signals here. This is a continuous convolution. Okay. Then let's start from -2. -2. Height of 1. So this is for our input signal. So for every input signal, of course, there will be an impulse response. Then we'll again base from time 0. So from time 0 here, okay, we will start from -1. Okay, 1 placed on the left side here. So 1 place, so we have -3. But since the input signal will start from here, okay, this will not spike before the input signal. It will not predict that the input signal will start here. Okay, so once the input signal is activated here, the voltage of the impulse response will slowly rise. Okay, it will be slowly rising because the input signal is here, not here. Okay, so the impulse response does not know that the input signal is from will start from -2. Okay, so since when -2 is activated, so the voltage from -3 will slowly rise until the input signal will have a pulse at -2. Okay, and then 1 times 1, so 1, 1, 1, 1, 1, 1, 1, 1, 1, until we reach 2. So from 2, okay, we still have 2 places on the right side, but there will be no more input signals. This is the last input signal, so the voltage will slowly die out. Okay, so that's why they're saying that the output of the rectangle is a trapezium because of this behavior of voltages. Okay, so again, this is the input signal. This is the input signal. Then this is the left side of our impulse response. This is the right side of our impulse response. This is the first impulse response, -2. So from -2, this will be activated. Okay, this will be activated. But since the impulse response should have a voltage before that, so the voltage will be slowly rising until the pulse. Okay. Then the last pulse will be at time 2. At time 2, since this is the last pulse, but the impulse response still has voltage on 2-time signals or 2-time counts at 2-time counts. But there is no more impulse signal. This is the last one. So the voltage will slowly die out. Okay. That's why the output of the convolution of two rectangles is a trapezium. This one. And the range is from -3 because of this left side and +4 because of this right side. Okay. So that's it for our limits. So we did two things at the same time, the limits and then the convolution of two rectangles. Next, we have the area of convoluted signals. Let's see first. Okay. So area of convoluted signal. The area of convoluted signal is given by the area of the output is equals to the area of the input times the area of the impulse response. Okay. So the proof is here. So this is the proof. Call this one. So from the working equation of our convolution, where y of t is equals to the integration of x tau h t minus tau d tau from -infinity to +infinity. Okay, so area integration, right? So if we will integrate y of t dt, we are taking the area of the output. Well, so we will integrate both sides. Okay, then we will separate tau and t. So tau will be on x, dt will be on h. So this is the area of the input signal. This is the area of the impulse signal. Again, integration area. You still remember, right? Good. Let's see if we have an example here. Nope, we have no example. Next. Oh, not included in the presentation. So next we have the DC component. So the DC component of any signal is given by, so DC component is equals to area of the signal divided by the period of the signal. So period or duration or the limit. Okay, so the period can be taken from our limits. We solve for the limits, we can solve for the period. We just subtract the upper limit minus lower limit. So here we have 4 minus -3, so we have a period of 7. This is our example earlier. Next, we will solve for the area. Okay, to solve for the DC component. So from the solution earlier, we have this one. The output is equals to the area of the input signal times the area of the impulse response. So looking at our signals here, we have this rectangle. The height is 1. The length is from -1 to 2. So this is 3. Okay. Next, we have a rectangle here. The length again is 1 as well. And then, or rather, the height is 1 as well. And then the length is from -2 to 2. So 4. So 3 times 4, we have 12. Okay. Again, area of the output, area of the input times area of the impulse response. So 3 times 4 equals 12. Then our period is from our limits earlier, which is -3 and 4. So 4 minus -3, 7. So the DC component is 12/7. Or, how much is 12/7? 12/7 is equal to 1.71. Okay. So that is for our DC component. If you want to prove the formula of area, okay, so we know that this area is 3, this area is 4. We'll solve for the area of the output. We can try this one. Wait. This area, the last topic. Oh, we still have a topic. Okay. We will try to solve for the area later if we have still time. So discrete convolution. I gave you an example of a discrete convolution earlier. This one. Okay. So what we did here is we solved, or we did the convolution for each input at time 1 and input at time 2. Okay. Then we added both outputs of each input signal for the total output. Okay. But we have another way to solve for the convolution of our discrete signals, and that is through tabular method. Okay. So here, for example, we have two signals, x of n with ABC as the impulse signals, and then h of n with EFG as its impulse signals. Okay, so what will happen here is we make a table. Okay, either of them will do. I mean, we can do x of n on top or h of n on the vertical. We can also do h of n on the horizontal and then x of n on vertical. So the answer will be the same. Okay, then we multiply each of the components. So E times A, B times E, C times E, A times F, B times F, and so on and so forth. Then we divide them with these lines and we add all of the components within the lines. So we have EA, EB plus FA, EC plus FB plus GA, FC plus GB, then GC. So this is the tabular method of our convolution signal. So I have another example here, this time with numbers, so you can see how the solution works better. Okay, but we have a note here. If any two sequences have n, have m, and number of samples respectively, then the resulting convoluted sequence will have m plus n minus 1 samples. So in this case, right, our input has 3 signals or three pulses. Our impulse has 3 pulses as well, so total of 6 pulses. The output will be m plus n minus 1. So 6 plus 3 plus 3 minus 1. So the output should be 5. So 1, 2, 3, 4, 5. Okay. So that is for the tabular method of our discrete convolution. So we have another example here. Convolute two sequences x of n with samples 1, 2, and 3, and h of n with samples -1, 2, and 2. So we will be using tabular method, or you can use this one. It's up to you. Okay, so if we will use tabular method, so 1 times -1, 2 times -1, 3 times -1, 1 times 2, 2 times 2, 3 times 2, 1 times 2, 2 times 2, and 3 times 2. Then again, we will separate them with lines and we will add all of the components within the lines. So -1, -2 plus 2, -3 plus 4 plus 2, 6 plus 4 and 6. Then we simplify. We have negative 1. We have 0, 3, 10, and 6. So this is our yn. So here, xn contains 3 samples, and hn is also having 3 samples. So the resulting sequence having 3 plus 3 minus 1 equals 5 samples. Okay?